Alright, it's time to take a look at one of these volumes of revolution. And number 9, there are many, many ways to rotate this, and it gets kind of complicated depending on how you, what method you choose. And you're probably wondering, which method do you choose? You kind of have to, in the beginning, try them both until you realize the benefits of one over another. So 9A is a great place to start. So we'll start with that one, and we'll check. In this particular instance, we'll start with washer, which will end up being the easier route in this case, and then transfer to shell. And we'll see that shell actually is the one that's a little more complicated if you should choose to take that route. Either way can work, it's just the amount of work that you want to put in to make it happen. So first thing you want to look at is the region in question. So I've got this is rotation on x-axis in 9A, and so I've got a nice little rotational solid. Actually shows you what it looks like if you make that happen. And the region in question's in blue there. It matches what's up above. You see in that graph, and so you can see kind of the match between these two. There should be anyway. If there isn't, then you let me know. But that's the main idea. And this, if I'm going to use the washer method, if you remember, outer radius squared minus inner radius squared times pi, and you integrate on the region from the lowest. In this case, we're doing dx because we're going around the x-axis, and x-axis rotations with washers are always in terms of dx, and the functions are in terms of x. And you do outer radius, which I've done in red. I've color-coded this a little bit, and you can see it's the distance from the axis to the outer edge, and inner radius is the distance, and I have it in yellow there, from inner edge to the axis of rotation. What we're going to do is have two little subtraction problems to represent those radii being squared, respectively. And what they are for the outer radius, it's the x squared plus 1 function minus 0. Remember, 0 is our axis of rotation. And then the inner edge is x, and then subtracting 0 again to create the distance from the function to the axis of rotation, 0 squared. And we're done. 0 to 1. We can integrate that. So it's always, remember for these, it's always function minus axis or axis minus function for the radii. And it depends on which one is on top always goes first, or to the right always goes first if you're rotating around something parallel to the y-axis. So down below, let's simplify this a little bit of algebra to get these down to simpler terms. I can distribute out that x squared plus 1 to take it a step further, and then you get a nice polynomial, some like terms, and this is a very clean looking little antiderivative. We're going to do it with a pi out front and take it from 0 to 1. It's about 23 pi over 15, 4.8171. Slick with washers. Now, this next is I'm going to show you the shell method. This would be a great way to give you a sense of how the shell method works, because you actually have to use two of them, but it's not efficient. And actually, I think I want you to explore the idea that what method you choose, the amount of work that it takes, actually explains a lot about the benefits of one method over another. So the shell method is always 2 pi times the radius times the height of these cylindrical shells. And shells are actually, rolls of toilet paper in a conical region. So if you can think of it, if it's standing upright, it's kind of a cone, and it's hollowed out. It's one piece of toilet paper rolled up. So it can be very thin. And then if it's on its side, likewise, it looks very similar. Okay, so if we take this, for this particular instance, this one's going to be dy, because a dx shell is rotated around the y-axis, and a dy shell is rotated around the x-axis. That's the opposite of what we've been doing in the past. In fact, I might put a little diagram up here. So if it's a vertical shell, that's going to be dx. And if it's a sideways shell, like this one here, let's see if I can make it halfway decent looking cylindrical shell. Remember, it's just a cylinder. This is a dy shell. And what it is the thickness of that piece of paper. How thick it is, how it's measured, is in x width terms. How thick this piece of paper is over on the right is measured in dy terms. How thick a slice of that toilet paper is a y thickness of some kind. Okay, so that's where that's developed from. All right, to the next piece. So we are doing it sideways because, in this particular case, now over onto the side, I think I went a little bit too far, so let me back up just a tad bit here. So I got it in terms of dy. Got it, clear that out, bing, bing, bing. Okay, now the next thing I'm going to do is put that roll of toilet paper in there just for diagram's sake. I think I kind of went past that. But if you look over on the picture, there's your toilet paper roll. And remember, this would have to be a little bit bigger toilet paper roll than I've done in this picture. But I could carve it out to make it look like this cylindrical shell. For us, our radius is the distance from the x-axis to some internal region within the axis of rotation. So we're basically the radius in a shell is always the distance from x-axis to some piece, one of the cylindrical shells on the region of integration. So each roll of toilet paper is a different length, and it's a different radius to get to that. And that radius is always somewhere from your lowest y, of your region of integration, to the highest y of that region of integration. But you always have to subtract that with the axis of rotation to get the actual distance that we call that radius. That's the component of a cylindrical shell. So for ours, in this particular case, it's y, because it's a distance from axis of rotation, and it's vertical to the region of integration. So in that distance y, there is a unique rolled up piece of toilet paper with also a unique height. So that's just the radius to get you to that unique piece of paper. And what that next component is I need to know the height, how tall that roll of toilet paper is. And remember what we did in classes, we would unravel these and look at them as a kind of rectangular piece. And so if I take one roll of this toilet paper and unravel it, it is a rectangle of sorts. Its thickness is dy, but it unravels this length here on the side. If I give you just a little dimension here, this tall dimension here, that's the 2 pi r. So it'd be 2 pi times radius y. That's this piece right here corresponds to the height or the length of that piece of unrolled toilet paper when we're talking cylindrical shells. Okay, this width here that I'm showing in this particular picture is how thick it is, or kind of how wide it is, and that's dependent on the two functions that create this. And that comes from this piece right here. That's your height that I put in there. And then dy is the thickness of the toilet paper. Okay, so I'm going to get those lines out of there because it's a little too much to look at, but we'll keep rolling. So in this particular case, the function that makes that inner edge, and I'm going to draw lines to this too, so you just want to watch out. I've done it in red here so you can kind of see it. It is right here, this y. This is the line. Now it's y equals x, but since we're doing it in terms of y, you want to think of this as x equals y. And so that's why, no pun intended by the way, that I do y minus 0 is the equation describing that yellow inner edge. That's the height, the distance between that red slanted line, which is the function y, in terms of that particular function, and then that yellow line, which makes the bottom end of it, that the height of any piece of toilet paper that's rolled up in that region is always going to be y minus 0, the right minus the left of those two. Okay, I'm going to get rid of those lines again because it's just too crowded to look at. Okay, got them out, 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 and gone. On to the next piece. Now that region right there, we'll call it our A region. We just got, that's the first, if we do 2 pi 0 to 1, that's the height that region ends at. The radius is going to be y in that region, and the height is going to be y minus 0. That's going to give us that shaded A region, its volume that you rotate around. It'll spin it out. But then I have to do a second integral from 1 to 2 with that also has a radius of y. So the radius is always going to be y minus the axis of rotation, or axis of rotation minus y when you're doing it around the x-axis. And so ours is just going to be y. And the height in that B region is going to be that purple. You see I've marked it, I've color-coded there. That purple x equals 1 line back to the orange curved line, which is in terms of y, it's the square root of y minus 1. So that's the height that goes with that component. Every piece of toilet paper is described by 1 minus square root of y minus 1 will give you the height of a cylindrical shell in the region from 1 to 2 that you see there, that B region. Alright, if you want the volume of those, you add them up, and then we get the total volume. So it's a big crazy mess. You put those two together, and you get the cylindrical shell method to getting the volume of that particular rotational thing. I think if you're, I think you might be on the same page with me. I think I'm going to go with the washer on that one. What you're going to find out is, I think if you're noticing, is that the components that make up washer method are outer radius squared minus inner radius squared. The way you measure the outer radius and inner radius, if it's a consistent function that's always the top minus the bottom or the right minus the left in your washer method, choose washer method. If it's a consistent function that describes the height that you have in the shell method, like in this case, if you look at my A region and my B region, they don't have they have different heights, ways of measuring the height. that's going to create a need for a second integral. And so that makes it less efficient because there isn't a consistent way of measuring that particular dimension. You had to do two integrals. Okay, so that's how you get through A. I'm going to do a video then for each, a couple of them that are most interesting in here, and send those your way as well.